For this experiment, we are talking about equilibrium. So I have here potassium chromate and potassium dichromate, and I've put them in a spot plate. And what I'm going to show you is that if we add dilute hydrochloric acid, we can alter the equilibrium of these chemicals. So here's I'm going to leave number one as empty. I'm going to do a little bit of hydrochloric acid in the second well plate. And notice that it starts to turn orange, and that's because the potassium chromates are in equilibrium. Notice that if I add more hydrochloric acid to the potassium dichromate, it retains that orange color. So the orange color is when it can be formed by adding hydrogen to the hydrogens to one side of the equation. You can shift the color in the other direction. Now, the opposite of adding an acid is to add a base. So here I'm going to add some sodium hydroxide to my dichromate. Notice no effect, or to my potassium chromate. But if I add some hydrochloric acid to the dichromate, I see an instantaneous change over to the yellow solution. So that's an interesting sort of observation you can make, and we could actually bring these solutions back just by switching the chemicals. So if I wanted, I can add some more hydrochloric acid, but now add it to the one that I just added the HCl or the OH to, and the chemical will shift back, and I can shift it back again. So here I am playing with forcing this thing to find a new equilibrium. And if you even watch it very carefully, you'll actually notice that the point where this touches, there'll be an instantaneous change, and then it will spread as equilibrium spreads across the solution. And it reaches the new equilibrium point, which has more of the orange or more of the yellow compound in it. Now, we can also force this chemical reaction to move in different ways if we create side reactions. So for example, barium nitrate has a reaction with chromate, so the yellow compound. And so let's see what happens if we allow the barium to react with that chromate. We see the formation of a solid precipitate. And so if we keep going, nothing too exciting. Okay, so a solid precipitate forms. Now, that means that it's actually taken some potassium chromate and converted it into a solid form. So let's see what would happen in the dichromate if we add the barium. Sort of no effect on the dichromate, because remember that in the dichromate there are very few of these chromate ions floating around. And so could we reverse this reaction? Well, actually no, it should not be. Barium chromate is supposed to be a solid. Oh, but I added barium nitrate. Okay, good. Okay, so that's why. Yeah, very good. Okay. Just going to flip the page. So we can notice that what we really want to notice here is that the barium dichromate, or barium chromate, is not very soluble at all. It turns into a solid right away, but the dichromate is soluble. So I wonder, I want to try one thing. What about when we added, let's see, I think we added the HCl, correct? No, we added the hydroxide. Let's add a drop of hydroxide and see what happens. Nothing too much, nothing too exciting. We add a drop of hydroxide in this one. Of course, we start to see the formation of that solid barium chromate as the barium chromate as the equilibrium of the potassium dichromate shifts towards the potassium chromate side. That potassium chromate instantaneously reacts with the barium that's floating around solution to form that solid. So let's try one more thing. I want to see, that was adding hydroxide, so that means that if I add some hydroxide, I should be able, or some HCl, I should be able to reverse this process, and let's see how that goes. And there you go, look, I can make the solid go away by using an acid. Although there is a little bit of barium dichromate, I believe, there in the bottom. It's not nearly as clear as it was a second ago. Oh, no, it's pretty clear. So that's equilibrium. We're just playing with it. We're playing with it by manipulating it, and we'll talk in the following video or the follow-up section about what these chemical reactions must look like.